A variable is said to be discrete if this variable is actually countable or finite in nature. That is, we can have the variable of number 1, we can have variable number 2, we can have variable number 3, 4, down to like wherever we want to stop. So that means, for example, we can have just one car in our compound, we can have two cars, we can have three cars, we can have four cars. So whenever this variable that is countable, that is discrete, now have a probabilistic value attached to it, then we have what we call a discrete random variable. Now, the mathematical distribution that helps us to calculate the probabilistic value attached to any discrete random variable is what we call a discrete probability distribution. There are several types of discrete probability distributions. We have the likes of the Bernoulli distribution, we have the binomial distribution, we have the Poisson distribution, we have the negative binomial distribution, we have the hypergeometric distribution, just to mention a few. Now, I've actually made a video separately for the concept of discrete probability distribution. I will be linking that playlist and most of the videos in the top right corner and also in the description. You can just check that video out after watching this video. But today's video is all about the concept of the continuous probability distribution. For us to understand the basis of the continuous probability distribution, we have to go back and understand what a continuous variable is, and then we'll move to the concept of the continuous random variable. So basically, a variable is said to be continuous if it is actually infinite. Please recall that for a discrete variable, it can take a single value, that is 1, 2, 3, 4, 5, 6. Unlike the discrete, the continuous variable can never take a countable number. They cannot take a distinct number. They are usually within a range of value, meaning we have the minimum value and we have the maximum value, and the continuous variable is always within a specified interval, and that leads to the second property of a continuous variable, and that is the fact that it is measurable. Now, the discrete variable is actually countable, but the continuous is not countable, it is measurable, and because it is measurable, it means it can actually take decimal values, because it can stand in between values. Your discrete variable can never take a decimal value. Examples of variables that are actually continuous in nature: we have the likes of speed, we have the likes of pressure, we have the likes of height, we have the likes of acceleration, just to mention a few. When we have a random scenario, we have a random experiment, and a continuous variable is as a result of this random experiment. So we are going to be having a continuous random variable, and that is because a probabilistic value would be attached to this random variable, and that makes it a continuous random variable. In today's video, I'll be talking about the mathematics that defines a continuous probability distribution. I won't be touching the various type of continuous distributions, such as the normal distribution, the uniform distribution. That would be in a separate video, but today's video is all about the mathematics and the nitty-gritty of the concept of the continuous probability distribution. I'll be talking about the expected value, the variance formula, the standard deviation formula, the probability density function, and the cumulative density function that defines a continuous probability distribution. I have to be honest with you, this video is going to be a bit mathematical, because I'll be introducing some calculus, one or two, in there. So I'm bracing you up right now, but uh, I will try to make it as simple as possible for you, so that you can actually get the detail in the simplest way that you can. Now, when the continuous random variables come together with the probabilistic value attached to each of them, then we have what we call a continuous probability distribution. Okay, so we have several types of continuous probability distribution. We have a lot of them. I'm talking about the likes of the uniform distribution, the normal distribution, the exponential distribution, the t-distribution, the chi-square distribution, the gamma distribution, between the bars of an histogram. And secondly, the histogram is not dependent on the height of the bars. Rather, the histogram is dependent on the areas of the bars. That is the reason why for an histogram, each of the bars can have different areas attached to them. And that is because, when you're working with an histogram, you can have what we call in the intervals, or we can have what we call the class or the bins, okay? And these bins can vary from one point to the other. A single variable can have between 0 to 5, the next can have like 5 to like 8, and the next can have like 8 to like 15, and we have like 16 to like 20. The class width or the class interval for a histogram is actually going to be varied, and since the class width or interval can actually vary for an histogram, so the area of the bars that defines a histogram can also change. That simply implies that the histogram is defined by the area of the rectangle, but the bar chart is defined by the height of the rectangle. So for a bar chart, the areas of the bars are actually constant, they're actually fixed, but the heights are different. But for an histogram, the areas of the bars or of the rectangle are actually different, and the heights are also different. So when it comes to a histogram, we use area to define the histogram as a whole. So when you plot the histogram for a continuous random variable, there is obviously a total area under the distribution. There is actually a total area under the curve, and that is going to be 100%. That now leads us to the reason why we can't be able to say probability that x is equals to 3.2, x is equals to 3.5 when it comes to continuous random variable, but we can say probability that x is between 3.2 and 4.5, x is between 5.2 and 7.3. But for a bar chart for a discrete random variable, we can just say probability that x is equals to 3, we can say probability that x is equals to 5, and that's because each of the bars are distinct from each other. But for a histogram, the bars are not distinct, they are actually smeared, they actually come together to form a single area. I hope that actually makes sense. Let us talk about how we can calculate probabilistic values attached to a continuous probability distributions in general. Let's assume that we actually have a random variable x that is defined by a continuous probability distribution, and we use an histogram to actually visualize this continuous random variable. So let's assume we have our histogram, okay? There is obviously a total area under the histogram as a whole, and there is a mathematical function that defines the probabilistic value attached to the random variables that makes up the probability distribution. So for a continuous random variable, if you want to calculate the probabilistic value that a single random variable is located within two intervals, all you have to do is to calculate the area bounded by those intervals. That way you'll be able to calculate the chance that a single random variable is going to be within that calculated interval. So let's say we have interval A and we have interval B, and we want to get the probability that a random variable x is going to be located between point A and point B. All we have to do is to calculate the area bounded by point A and point B, and we would be able to calculate probabilistic value that a random variable x is located between point A and point B. From basic mensuration, we know that the formula for the area of specific shapes actually changes. The area of a triangle is different from the area of a rectangle, that is different from the area of a circle, and details like that. But the shape that most probability distribution gives to us are actually not triangle, circle, or something that we can actually quantify with mensuration. So that means a bit of integration is going to be introduced to help us calculate the area of a specific shape. So whenever we have a probability distribution, a continuous probability distribution to be specific, and we have two boundaries, let's say boundaries A and B. Now the mathematical function that defines that probabilistic distribution is very important to us in calculating the probabilistic value that a single random variable x is going to be located between the values of A and B. In simple terms, that function is important for us to calculate the area bounded by point A and point B. So according to integration, if I have point A and I have point B and I have a mathematical function f of x, for example, that actually defines that defines the distribution as a whole, then the area is equal to the integral of B, we have A is equals to f of x times d of x. That is the formula for area according to integration. So that simply implies that if you want to get the probabilistic value that a random variable x is going to be located between the intervals of a and b, then the probability of getting the random variable x located there in a and b is given as probability of into bracket a, we have lesser than x and lesser than b, and it's going to be equals to the integral of b a, we have f of x times d of x. Now where f of x in this case represents the probability density function that defines the continuous probability distribution. So if you want to calculate the chance that a single random variable is going to be located between two intervals, then we have to get probability density function that defines that distribution, then have these two boundaries, then take the integral over that boundary to get the area, and that area that you are getting is actually the probabilistic value that the random variable x will be located between points A and points B. Please note that whenever you want to get the probabilistic value that a continuous random variable x is located between points A and B, you are going to be needing the f of x, and then you will be taking the integral over the area. So in summary, to get the probabilistic value attached to a continuous random variable, an area needs to be swept, meaning you are going to be starting from somewhere and you must actually end somewhere, probably A and B, B and C, but you must actually sweep a specific area. There must be an area, an interval that you are actually interested in. I'm sure you want to ask me this question: what if I have a question that goes like probability that x is actually lesser than or equals to 4? How do I get the probabilistic value attached to this this kind of question? Is an area being swept? Yes, definitely an area has actually been swept, because x lesser than or equals to 3 means from 3 we have 2, we have 1, and we have 0. So probability that x is lesser than or equals to 3 is still an area, so that means we need to take an integral from one specific region to another specific region. So that means probability that x is lesser than or equals to 3 is equals to the integral. So we start from the upper limit, which is equals to 3, and we have the lower limit, and then in this case we won't be using f of x, which represents the probability density function. We are going to be using f uppercase f into bracket x, which represents the cumulative density function, and this way we are going to be able to get probabilistic value that x is actually lesser than or equals to 3. So in summary, whenever you find yourself in situations such that you actually have a continuous probability distribution and you want to get a probability that a is lesser than x is lesser than b, that is, you're trying to see the chance of a random variable x located between point A and point B, then you're going to be taking the integral of the probability density function over the intervals b and a. And if you find yourself trying to answer a question like probability that x is lesser than or equals to a, that is trying to get the area between a and a lesser value, you're going to be taking the integral from a down to 0, and you're going to be using the cumulative density function as the mathematical function that defines that scenario. Just like the discrete probability distribution, we can also get the expected value, the variance, and the standard deviation for a continuous probability distribution. So let's say we are interested in getting the expected value for a continuous distribution, and we have the boundaries to be from minus infinity to infinity, and we are interested in the fact that a random variable x is located between these boundaries. So how do we get the expected value attached to this random variable within this boundary? The formula is going to be e of x, which represents the expected value, is equals to the integral from plus infinity to minus infinity. Then we have x times f of x d of x, and this is the formula that represents the expected value of a continuous probability distribution. Obviously, if we have the boundaries to be b and a, you just replace plus infinity and minus infinity with b as the upper limit and a as the lower limit. The formula for the variance that defines a continuous probability distribution is given as v into bracket x, that's the variance, or you can use sigma squared into bracket x, anyone you want to use, is equals to, we have x minus mu all squared. Now the mu in this case is representing the expected value, it is representing the population mean. Then we have times f of x dot dx, where the f of x in this case represents the probability density function, and the standard deviation is actually equals to the square root of variance, which simply implies that if you want to get the standard deviation, try and get the variance first, and this is how you can get the expected value, the variance, and the standard deviation of a continuous probability distribution. I hope I've been able to explain the mathematics that actually defines the continuous probability distribution to you. If you learned something new from this video and you actually enjoyed this video, please give this video a thumbs up and also subscribe to this YouTube channel. Do you think I missed something or you have some questions for me? Don't hesitate to go down to the comment section and drop your question. I would be willing and be ready to attend to all of them. Thanks for making it to the end of this video, and we'll see you in the next one. Bye for now.